illusions hold a very special place, in part because they're so surprising. You take a look at them and you expect to see one thing and something else happens. They tell us something deeper about our perceptual world and what it is we see. And that's a big question, because the question that we see something, that we see colors, we see objects, is something that we take for granted, but it really is a deep philosophical problem that has plagued or sort of been a central question for humanity since we've started thinking about what we are and who we are and what we do. So the real question is about reality and the nature of how our brains interpret reality. Here, there's a single dot traveling back and forth on a straight line. Now I'm going to add another dot, so there are 2 dots traveling on a straight line. And here are 6 dots, all traveling on straight lines. If I change the phase of the orange dot is still traveling on a straight line, still traveling in a straight path. And the red dot, again, still in a straight path, same timing as all the other dots. It's just that the phase of its modulation is different. Here's the purple dot, the yellow dot, and the green dot. Now, if we move the guides, we can see that the dots are organized to form a circle. So each dot by itself would be seen as traveling on a straight line. But taken together, all the dots are traveling as something more than what you would expect to see, traveling as a circle, moving around. So in the Tuesday illusion, we have a conflict between a dot that moves in a straight line and the society of dots. So that's how the dots are organized. But conflicts like this exist all over the place. For instance, in the wagon wheel illusion, which is something everybody's seen, I'm sure you see an old movie with a stagecoach and the stagecoach starts moving off one direction, but the wheel looks like it's spinning in the opposite direction. Well, if you play games with that type of illusion, you can start seeing how there's conflict embedded even in the simplest of image. Here we have an example of the wagon wheel illusion. There are 5 rings, each with 12 dots. The dots are separated by 30 degrees of angle. If we start to rotate the ring, it starts moving slowly in a clockwise direction. If we go faster, at 15 degrees, it's as if the direction of the ring can't make up its mind. Now, if we move the ring a little further, the ring starts going backwards. And if we go faster still to 30 degrees, the motion actually stops. And that's because it's always ambiguous. In this case, even though the ring is always spinning in a clockwise direction, each dot moves and falls on top of the other dot. And when that happens, the visual system has to make up its mind. Is it rotating clockwise, or is it standing still? And of course, standing still is a much simpler explanation, so you don't see its motion. If we were to move it at 27 degrees in one direction, that's the same as moving 3 degrees in the opposite direction. It's ambiguous. The visual system has to make up its mind, and it chooses to go, choosing, of course, being a rather funny term for this, it perceives the motion going backwards because it's a simpler process. We can play games with the ambiguity by changing the color of the dots because that gives away the game. So here, one of the dots in each ring is yellow. When we start moving it forward, you can always see the direction of the yellow dot. Here we go at 5 degrees in the clockwise direction. All the dots are moving together. At 15 degrees, that was when the ring could be going clockwise or counterclockwise. In this case, we see the yellow ring always going in one direction, but we can't really pick out which direction the black dots are going. As we go faster, the separation begins. The black dots start going backwards. The yellow dots start going forwards. The Tuesday illusion and the color wagon wheel illusion show a conflict between two different sorts of information. So in 2Z, it's dot traveling in a straight path versus grouping as a circle. And in the color wagon wheel illusion, it's showing motion for change detection versus feature tracking. There are other illusions which combine more than one features. Some of my favorite illusions are ones which combine multiple features and multiple types of conflict in the environment, or tap into different processes in the brain. And the combination of the effects often creates really compelling illusions that everyone likes to look at. Here is Jeremy Hinton's Lilac Chaser. It's a wonderful illusion. There's no real motion here. All you're seeing is a dot turning off and turning back on, but it creates the impression of a dot traveling around the circle. In addition to that, when the magenta dot turns off, you are left with a green afterimage. That green dot is entirely constructed in your brain. Then the third illusion is something called Troxler fading. And this one takes a little practice. But if you fixate directly at the center of the screen and make sure you keep your eye as steady as you possibly can, then the pink dots will start to fade into the background as if they're not there at all. And that relies on the idea that in order to see things, we have to have edges. Your eyes have to move across edges. And if you get rid of those edges, then things begin to fade. The game is both to create these types of conflicts that make it really compelling to look at, and then try to narrow down the different conditions so that we can understand the processes that underlie them. Well, here's an illusion which shows that just because you sense something doesn't mean that you will perceive it. I just love this illusion, referred to as motion-induced blindness. It is a truly compelling illusion, and the first time you see it, it's hard to believe that it's actually happening. If you stare at the green dot in the center, you will see something remarkable happen. You should start seeing the yellow dots disappear. The dots are always there. They're always making an impression on your retina. There's always light coming from there, reaching the back of your eye, and your rods and cones are picking up the light, and they're turning into a signal that your brain can interpret. But for some reason, possibly due to attention, the dots just go away. They're just gone, and it's really compelling. So, do you know why this happens? I don't either. One would think that the easiest thing that we could explain was how bright an object is, right? The light comes in, the more light that goes to our brain, the brighter the object looks, right? Turns out that's not so simple. And next time, we're going to talk about different illusions which play games with how the brain constructs the perception of brightness. So for example, here's Ted Adelson's famous checker shadow illusion. We have two squares, one labeled A, one labeled B. A is dark, B looks light. But if you were to put the two squares right next to each other, you would see that they are identical. How can that be? here's Adelson's famous checker shadow illusion. As you can see, one of the squares is labeled A. It's a dark square outside of a shadow. And there's another square labeled B, which is a light square inside of the shadow. If we take the squares and pull them outside of the display, we can see that the two squares are identical to each other. The conventional explanation is we have two squares, one square sitting in a shadow, another one that's in direct illumination, but it's sitting in a dark square. And the visual system figures out this calculation based on all the experiences it's had in the past and what it thinks about what's happening in the world. I don't think that that's a really complete explanation. If you think about the brain as a type of filter, it knocks out some type of information. And I think much of what we find in these type of illusions can be accounted for by just getting rid of the coarse scale or the blurry information. From this point of view, Adelson's illusion and many other brightness illusions aren't necessarily illusions. The effect just sort of appears. Here we have a collection of shaded ovals, bright on top, dark on the bottom. As you can see, all of these, let's call them eggs, are identical to each other. Now, let's change the context in which they're presented. All I'm going to do is add a background to them. Once you add a background, the columns that fall on the dark part of the pattern start looking white, and the columns that fall on the white part of the pattern look darker. So instantly, the moment the background appears, our conception of brightness, our conception of the material, and the conception of what we see changes because of the context. We can do more than that with this demonstration. So if we slide the background to a different phase so that ones that were on the dark part now are on the light part, we can make them change again. So the ones that were white become dark, and the ones that are dark become white. So I can hear it now. Oh great, another one of those academics telling me that white's black and black's white. But in this case, yes, I'm doing that. And as you can see, I'm not telling you that white isn't white, but I'm telling you that depending on the context that you present something, you can make something look white or dark. It's really compelling and fun to watch the eggs change their appearance. But there are lots of tricks that vision scientists can use to make the effects look stronger. So if you take two gray patches that are identical to each other, and you place one on a white background and the other on a dark background, you can see that the one on the white background looks darker than the one on the dark background. Now, this effect is a standard simultaneous contrast illusion, but it's been known for quite a while that if you take a tissue paper or something semi-transparent and place it over the display, you get a really strong effect. So for instance, here is a semi-transparent brick pattern. Suddenly the difference between here and here becomes really strong. And there's nothing special about the brick pattern per se. You could use curtains, or you could use a wavy kind of blue-green pattern. Simply by adding these semi-transparent layers, we can accentuate the simultaneous contrast effect to make it look really strong. Here we have a design which I made based on a design by Kafka, a Gestalt psychologist in the early parts of the 20th century. The design has a number of colored squares, and in them are two half circles. The half circle on the right tends to look brighter than the design on the other half of the square. But if you start lining them up, you can see that the two halves are identical to each other. Once again, we have a brightness demonstration. You take two patches with the same luminance and put them in different contexts. One will look darker and one will look brighter. But in this case, we've added to it hue, so we can have different colors. And while you'd like to think the colors are changing, what you still have is a brightness effect, even though it's mixed with color. But there's another aspect to any display that you see, which has to do with the display's contrast. What I'm going to show you next is a demonstration that shows that contrast response is fundamental to how we see, and it sometimes takes precedence over color itself. Here we have two discs modulating in synchrony with each other. Now, I'm just going to change the colors of the surrounds and see what happens. Most people will look at the display and say, oh, they're alternating. They're going out of phase with each other. And in some respects, they are. So let's try it again. Here it is without the rings. Here it is with the rings. Most people see it as going out of phase. You can see that the discs are modulating in antiphase, but are getting white dark at the same time. It's as if there are two sources of information. One source of information corresponds to the luminance. It's getting brighter or darker, brighter and darker. The other source of information is the contrast. So when the discs are both bright, the one with the yellow ring has low contrast. The one with the dark ring has high contrast. When the discs are dark, the contrast relationships is reversed. So there you have it. Two sources of information, and the brain's not stupid. It can see both of those. Once you realize that the contrast information is something processed by the brain, there are a lot of fun games you can play with it. One of them is, can you use the contrast response, the brain's response to the contrast, to generate a motion signal? So let's take a look at this display. Here we have two rows of 5 discs. The row on top, the discs are going from dark to white and then snapping back to dark. On the bottom, the discs are going from white to dark and then snapping back to white. Right now, they're presented against a uniform background. There's no change in the contrast of the discs. If we make the background a gradient, though, the contrast will be different for each of the discs. As the discs change, the contrast changes across the discs. If you track the part of zero contrast, so imagine the gray parts of the background, when the disc goes from dark to white, the place in the middle where it's the same luminance as the background, that has zero contrast. Now the point of the zero contrast will be shifted over slightly in time when you have different brightness levels of the background. So what we're seeing is the visual system tracking the point of zero contrast and creating a motion signal from that transition. So this type of effect tells us about ways that the visual system can construct motion. The discs themselves aren't moving. The colors themselves aren't moving. The only place where there's a change in space over time is the contrast of the discs relative to the background. So one interesting question, of course, is that if you're trying to figure out where motion comes from, if you see a Las Vegas light blinking, are you tracking the colors of the lights, or are you just tracking the changes in the contrast? Context effects can occur for changes in color, not just for changes in brightness. Here we have a large grating. The grating itself is a mixture of 2 different gratings, one which is yellow and blue, another which is kind of cyan and red. If we split the grating into 2 small strips, we can see it by themselves, and the strips look identical to each other. If you surround the top strip by a yellow and blue grating, it will accentuate the red-green portion of the inner grating. If you surround the other strip by a red-green grating, it will accentuate the yellow-blue portion of the bottom grating. Those 2 little strips, which were identical beforehand, now appear quite different from each other. This is a beautiful effect. As the larger gratings drift across the screen, they're changing their induction within the smaller strip. So the colors that are being nulled move along and leaving the remaining colors, which are accentuated and different between the two strips. So next time we're going to talk about motion illusions. Motion illusions are fascinating because they play with the brain's ability to extract motion from the world. There are lots of ways to fool the system. Take a look at this one. Here we see a disc dropping from the top of the screen to the bottom of the screen. But look what happens when you look to the side of the screen. Are you looking? It's called the curveball illusion. We'll talk about it next time. We're going to talk about motion. We take motion for granted because we see things moving all the time. You're driving a car or you're walking. All of those involve an object, sometimes you, changing position from one location to the next. And it's a simple idea. All it takes is one object moving from one place to another place. But like everything else we perceive, the brain constructs motion. It does so in a way that's very useful for you, but the sense of motion is something that the brain does. And when you talk about a motion illusion, what you're doing is triggering that brain mechanism that creates the sensation of motion. In order to convince you that the brain is constructing motion, we're going to start with an illusion which I refer to as the curveball illusion. Here you see a ball dropping from the top of the screen to the bottom. Inside the ball, there's a pattern shifting from one side to the other. If you look directly at the ball, you can see that it's dropping vertically, and you can see the inside pattern spinning. But look to the right. What do you see? Most people report seeing the ball falling at an oblique angle. For fun, look off to the right, wait till the ball gets about halfway down, and then shift your eyes back toward the ball. You'll see the ball falling at an angle and then suddenly snap back to the vertical. Your central visual system processes motion differently than your peripheral motion system. It's as if your central motion system can separate both the vertical and the horizontal motions and see them both at the same time. Your peripheral system doesn't have to worry about all that detail. So it combines the motion signals, and it's as if you're adding them together to create a motion that's moving off at an oblique angle. There are many ways of configuring the illusion. So for instance, here's one where instead of having constant motion in one direction, I change the motion so that it accelerates in one direction and then switches back to the other. Now, if you look in the periphery, the ball will drop like a zigzag all the way down. The zigzag results from your peripheral system's inability to separate the downward motion from the horizontal motion. Just for fun, you can make the same effect by having the ovals go in a circle as opposed to dropping down the screen. Here, the ovals are rotating counterclockwise, and the internal signal is rotating clockwise. If you look off to the side, the display seems magically to rotate in the opposite direction. So the curveball illusion shows that different parts of the visual system process the world in different ways in order to extract motion. Now let's look at ways to create motion illusions just by changing the interactions of objects with their background. Here we see a collection of ovals. They are all completely stationary. Now let's see what happens if we change the background. What do you see? Do the ovals look like they're bobbing up and down? Let's see it again without the background. With the background. The reason the ovals appear to move has to do with the contrast between the ovals and the surrounding field. The ovals are shaded from white on top to dark on bottom. The background is a series of gradings shifting from black to white, black to white. When a black bar goes behind the ovals, there is high contrast on top and low contrast on the bottom. When a white bar goes behind the ovals, there is low contrast on top and high contrast on the bottom. The result of switching the contrast causes the ovals to give that wobble appearance because contrast by itself can create the appearance of motion. So let's try to reduce the contrast motion down to its fundamental elements. Here we see a display with 4 squares surrounded by edges. In the top 2 squares, the centers remain constant, but the surrounding edges modulate from light to dark. In the bottom 2 squares, the edges remain constant, but the centers modulate from light to dark. As you can see, the squares appear to expand and contract. The change in contrast between the background, the edges, and the squares gives the brain information about motion. Now, the curious part is that the motion moves in different directions depending upon whether it's the edge that modulates or whether it's the square that modulates. So, just by changing the contrast relationships, we're able to make the squares look as if they're contracting or expanding. Now let's see what happens if we modulate the background also. In this image, the top edges are modulating opposite that of the bottom edges. By adjusting the timing of these edges, we can make the diamond look as if it's moving perpetually upwards. If we change the phase so that the right edges are modulating opposite the left edges, we can change it so that the whole diamond appears to move to the right. So it can move up, right, left, or down. And all we're changing is the timing of the edges. So there you have it. We can create motion even though nothing is actually changing position. The edges are just changing luminance, but they're making changes in contrast. And the visual system's able to integrate the contrast so as to create the impression that whole objects are moving in one direction or another direction. Simple to do, but what it means is that the brain is finding signals of contrast and turning that contrast signal into a perception of motion. But the really amazing thing is, it seems as if the brain can extract motion from the image even if we don't actually change the luminance of the signals. Here's a now classic visual illusion by the great vision scientist Akiyoshi Kitaoka. The illusion consists of a series of colors, black, blue, white, gold, repeated over and over again in a circular pattern. The circular pattern is then repeated many times to create this wonderful display. When you're looking at it, it feels as if the discs are spinning continually in one direction or another. If you notice, when you look directly at one point in the image seems to stop directly where you're looking at it. The illusion, therefore, is an illusion of motion in your visual periphery. Akiyoshi Kitaoka is a genius who's created thousands of these types of displays. Here's one of my favorites, the rice wave. It's as if there's a pattern of motion that bends the image so that it flows over it like a giant wave of motion. In addition to motion illusions, Kitaoka has also created a wide variety of illusions which show distortions of lines, shapes, and form. Here's one which is referred to as the bulge. It's called that because the object looks as if there's a bulge coming out from the center. But if you were to take away the dots, you would see that it is just a regular checkerboard with straight horizontal and vertical lines. In our next episode, we're going to talk about the classical illusions that are like the bulge. We call those geometrical illusions. When people talk about illusions, they often think about the classics. Geometrical illusions in which parallel lines are no longer parallel, object sizes appear to grow or to shrink, or lines that appear to become larger or smaller depending upon their context. Such illusions have captured vision scientists' attention for years because they tantalizingly hold promise to tell us about our brain and how we perceive the world. So here we have the cafe wall illusion. It's a fabulous illusion in which you have a series of black and white checkered squares, and they're separated by mortar. The lines created by the mortar are always parallel to each other. But if you align the bricks correctly, the lines suddenly appear to move at a whole collection of different angles. The illusion is called the cafe wall illusion because Richard Gregory, a famous vision scientist, found the illusion in the wild while sitting in a cafe in Bristol, England. The cafe wall illusion is a classic illusion. There are hundreds of illusions of this sort. In the 19th and early 20th century, German scientists, British scientists, and some American scientists created a whole range of illusions such as this. One classic example is the Zollner illusion. Here we have lines which all run parallel to each other. And simply by adding lines at cross angles to them, we can see the lines suddenly appear to diverge from each other. The lines that were parallel are now tilting left or right. Zollner illusion shows changes in parallel lines, but you can also make changes in the extent or the size of various objects. Here's a classic illusion known as the Mueller-Lyer illusion. There are two lines exactly the same length. Now we add arrows on the end of the top line and inverted arrows on the ends of the bottom line. Most people think the bottom line now appears much bigger than the top line. There are many theories for why this illusion happens. Some people think it has to do with perspective cues. So for instance, when you have a line that's facing with the inward arrow, it's as if the line is closer to you because it represents the corner of a wall. When the lines face the other direction, it's as if the line is further from the observer because it's as if it represents the corner of a wall which is moving away from the observer. This type of explanation is really appealing because we know we construct depth from images, and we know that our construction of depth will change how we see the world. In the 60s, people used the Mueller-Lyer illusion to see whether the environment in which someone grows up would have an effect on how the illusion is perceived. So they went out to the Philippines and some areas of Africa to find cultures that didn't have buildings which would have sharp edges, to see if they could find whether the illusion existed in those environments. They figured that if there are depth cues embedded in the Mueller-Lyer illusion, depending on corners of buildings, but you don't have corners of buildings, then perhaps you shouldn't see this illusion at all. So they went out looking at these different places, and sure enough, that's what they found. Unfortunately, future studies didn't necessarily replicate their findings, and indeed the argument could be made that this is a perfect case of correlation and causation, right? Where they found a correlation where some places in the world seem to show the illusion to a lesser extent than others, and they wanted to propose that the effect is due to the building environment in which they lived. I tend to think that depth perception always plays some role in everything we do. But there are many variants of the Mueller-Lyer illusion, and these variants seem to create counterexamples that can't be explained by such a theory. Here we have two lines of the same length, but instead of arrows, we've attached circles to the ends. Same type of effect as you get from a Mueller-Lyer illusion. Or try this one, only made with dots. A theory based on misapplied depth cues would seem to have a hard time accounting for these variants of the Mueller-Lyer illusion. My guess is that for every geometric illusion, there are multiple factors going on. Depth may have some role, even though there are counterexamples. Filtering may have some role. But there is some type of power in the explanation of saying that when we see an object, if we interpret it as farther away, we're going to see it as bigger. Here is an example called the Ponzo illusion, also referred to as the railroad tracks illusion. Now, take two lines of exactly the same size, put one at the base of the railroad track and the other near the top of the railroad track. The one near the top miraculously appears as if it's larger than the one on the bottom. So these type of illusions can create a lot of fun effects because normally if a person walks into the distance, their retinal image becomes smaller and smaller and smaller. Now, if you cut out the picture of the person far away and you bring the image closer to you, that person seems comically small. This makes sense because if you're standing outside and someone walks away from you and they move into the distance, you don't suddenly say, wow, they're shrinking. What typically happens is you think that they remain the same size, but the image on your retina is becoming smaller and smaller. Another way geometric illusions make objects change size is by size contrast. So here's an illusion called the Ebbinghaus illusion. Two circles of exactly the same size. One is surrounded by small circles. The other is surrounded by big circles. The one surrounded by big circles looks much smaller than the one surrounded by the smaller ones. The Ebbinghaus illusion seems to show a size contrast effect. It seems to be a general characteristic of the visual system. Contrast effects such as these suggest that you're never really seeing an object by itself. It's always part of some context and some organizational principle. Why have such illusions had such staying power? We're still interested in them after hundreds of years. To paraphrase one of the early researchers on this topic, such illusions mock us in plain sight. We always are trying to explain them, and we've had some success, but the actual explanation is still open for debate. Next time, we're going to look at illusions that occur when objects interact with each other. What happens when you have one element and then add another element, and the visual system interprets them as if it's something new and different and creative. When you open your eyes, you take for granted that you see a world populated full of objects and people and things. It all makes sense to you. But if you were to look at the back of your eye and you see that there's an array of light falling on your retina, at the level of the retina, there are no objects. All you have is an array of light, changes in brightness, changes in wavelength. Somehow or other, your visual system has to make sense of all that information. And to do that, it makes assumptions about what it is we see. So take, for example, the Kinesia triangle. Here you have a blank field. And if you add these little characters, some people say look like Pac-Man from the old video game, if you line them up correctly, suddenly a triangle appears. It is as if the triangle is sitting on top of the circles. Your brain is filling in the triangle because when you line up the circles in that shape and the edges of the triangles match up, the best explanation, given this configuration, is that there is a triangle blocking out portions of the circles. We do this all the time, but most often in the world we have objects that we know about, obeying rules that make things easy for us to see the object. But what happens if the elements in the scene are more ambiguous than that, where it's not easy to piece together a story? You'll start looking at them and trying to make sense of an object. But once something appears, your visual system will stay with that. So take a look at this example. What do you see? Often your brain will search around and try to find objects. But if I tell you there's a cow in this image, will you be able to find it? If you've never seen this before, the object of the cow will be hard to see. But once you see it, your brain will forever be changed. Perceptual learning occurs. And next time you see this type of display, suddenly you'll be able to pull out the cow. Here's another example that contains an object that some people find hard to find. What if I tell you that the object is a dog? For people who haven't seen this before, the moment that they can see the dog is really quite surprising. It's as if the whole image has suddenly reorganized itself into something that makes sense. Your brain has changed. Now it knows when it sees these blobs, it can piece together a dog. So let's take a look at this display. Here's a bird made out of small little lines. Easy to see. But what happens if we add some background so the bird is camouflaged? Now it's very hard to see the bird, but your brain can track it as it moves back and forth. Now watch what happens when the bird stops. What do you see? It's as if you can see it for a split second, and then it just fades away into the background. Your brain's unable to distinguish the object from the noise. It's a funny thing. The bird is always there. The Dalmatian is always there. The cow is always there. It takes your brain organizing the information in a special way in order for you to be able to see it. The brain in your perceptual system is really creative in how it organizes information. It's active. If you think about things, you can reorganize them and juxtapose information in ways that you hadn't thought of before. So for instance, take a look at this display. Here are 4 lines, all moving in and out from each other. You can group them pretty easily as 2 bars going on one oblique angle and another 2 bars moving on the other oblique angle. But if we add some information, you can see something quite surprising. By blocking out the ends of the lines, your brain's able to fill in information to complete the object, to see a square moving about as opposed to 4 separate elements. The brain is always trying to make its best guess about what's happening in the world. Without the occluding squares, you'll see it as 4 different lines. But with the occluding squares, suddenly it's able to make a real simple image of the world. Here's another illusion involving squares, which also shows how the brain can construct a world from simple information. Look at this image. You see a plus sign expanding and contracting. Now, let's give a little more information by pulling back the occluding squares. Now, instead of just a plus sign, you can see that there's a square in the background. You can tell this because at certain points you see the particular angles of the square. But it looks as if the square is rotating and becoming bigger and smaller. Next, let's pull back the orange squares so we can get a better idea of what's behind them. It always surprises me when this is presented. Suddenly, the breathing square turns into a simple square turning about its center. A curious aspect of this display is that by getting rid of some information, things which we take for granted, sort of assumptions of objects being rigid and operating in the world not changing, goes away. So it's really clear that the square is doing nothing but rotating. But when we cover up the corners, we don't have enough information to see it as rotating. Instead, we see it as breathing. It's as if getting rid of the information overrides the basic idea that the square is a rigid square that's rotating. Our brain is always trying to give us a perceptual world that makes sense. It does this by finding the simplest rules that are available. This is the gestalt, the organization of what we see. There are many rules that guide our behavior. Some of them have to do with finding things that are similar. Some have to do with finding objects that move in a corresponding manner. Some have to do with how close objects are to each other. Sometimes grouping depends upon the contrast in the image. Because these dots are modulating together, we organize them as rows. Next, let's change the background to see how the brain organizes this display. Now the circles are organized along the diagonals. The top right groups with the bottom left, and the top left organizes with the bottom right, based on the contrast of the dots relative to their respective backgrounds. Our brains are always trying to make sense of the world. But sometimes the information and how we organize that information produces things which seem to conflict with each other. When that happens, it's always interesting to look at. It's always interesting to see, and it's often referred to as an illusion. An ambiguous image is one where the image stays the same, but our percept of the image changes. Could it be one thing or another? We often talk as if an image and our perception of that image are the same thing, but they're not. Light energy entering your eye is sensed by photoreceptor cells in the retina. Those photoreceptors transform the light into a format that the brain can understand. We call that format neural signals, the brain's method for moving electricity from one point to another. Millions of neural signals move from your eye to your brain every second. Most of those signals are sent via the midbrain to an area in the back of the brain called the visual cortex, located in the occipital lobe. From there, the neural signals travel to many different parts of the brain. Each area in the brain responds to different information extracted from the image. The brain first has to decide what is the object and what is the background. And this isn't always as simple as it sounds. Imagine, if you will, a blank screen, and you draw a line in one portion of it. That line forms a boundary. The line divides your perception of space. If we add another line here, we have what's known as Rubin's vase illusion. When you look at it directly, sometimes in the center you'll see a vase standing there as if by itself. And then you'll see the background appear as two different faces. So your perception is always switching, either the vase or the two faces. It's not as if the image itself has changed, only the way your brain constructs the world. It's as if our world is composed of these objects and we're always struggling to make one part of the scene real and the other part the background. This is particularly true with this classic Escher illusion. Here is a famous painting of his called Sky and Water. In this painting, near the top, you see primarily birds, and on the bottom, you see primarily fish. What he has done is to add detail to the birds on the top and add detail to the fish on the bottom. And by adding the detail, you've given those forms sort of an objectness that make them become more vivid and more object-like. Less obvious than Rubin's vase or Escher's birds and fish. Look at this representation of a cube. There are at least 3 ways of interpreting this shape. Most people see it as a cube with the lower front corner nibbled out. Got it? Now, look for a cube-shaped room with a small cube intruding into the far corner. Got it? And number 3 is a complete cube with a small cube joined to its near corner, at rather an odd angle. This one's a bit strange, not so easy, but it is there. Got it? The object stays the same, the world stays the same, but our brain wants to give it one of 2 or 3 different possible interpretations. It's not stable, not because the image isn't stable, it's because our brain is trying to understand it in different ways. So take a look at this object, attributed to 19th century crystallographer Louis Albert Necker. Not much to get excited about here, but which way is it facing? Most people first see it this way, as if the lower right face is coming out towards you and downwards. But this way of looking at the cube, with the arrow emerging from the top left forward-facing square, which appears to be projecting upwards, is just as valid. Look at it again without the arrows, and you'll probably find that your brain is switching from one angle to the other every few seconds or so, without you having to do anything. Your brain is trying to make sense of the conflicting messages it's receiving. So, at a certain point, we're not sure exactly when, the brain switches to the other view, which may be more satisfying or more stable. Of course, one view isn't more stable than any other view, but your brain doesn't know that. But there's a twist, literally. If we rotate the cube as if it's suspended from an invisible thread, the ambiguity continues as before, but now something else is happening too. Watch the rotating cube and just relax. Is it rotating anti-clockwise or clockwise? Or did it just change direction? Watch some more. Pick a corner. One moment it's going away from you. The next, it's approaching you. Did you consciously make it switch directions, or did it just seem to happen automatically? Of course, when the cubes rotate from one direction to another, it has to correspond to something that's going on in the brain. Perhaps it's a set of networks where one network dominates in one condition and another network dominates in another. But we don't know the specifics of such networks. In fact, when we do understand the specifics, we'll go a long way towards understanding what perception is and how consciousness occurs. Now, Necker's rotating cube is intellectually intriguing, but here's an image that has caught people's attention more directly. Kayahara's spinning dancer. If you watch the dancer, it'll seem to spin either in one direction or the other. For some people, it'll stay spinning in that direction for a long time. But if you watch it long enough, it'll reverse in the other direction. Why does this happen? Well, the information that's available in the image tells us that there's a dancer spinning. Because we don't have detail, we could easily interpret it as spinning one direction or the other direction. The information would make sense either way. The brain has to make a decision. So with the silhouette, we have a lack of information. It could be interpreted either direction. But what happens if it's something that's a familiar object with information? Here we have a mask. One that would be staring right out at you into the audience. But look what happens when it spins. It starts rotating to the right, but suddenly the face itself looks like it's spinning to the left. Why is that? You thought you were looking at a regular mask, but actually you were looking at the inside of a mask, and our brain flipped it so it was actually seemed like it was looking right out at you instead of looking away from you. Here's another way of playing with the same type of illusion as the hollow mask, which is Jerry Anders's wonderful dragon illusion. Here the dragon's faces are inwards, but you would never guess it from looking at this picture until you see the object rotate. And once it starts moving, suddenly we have different types of information that are available. And the faces seem to be moving in an opposite direction of the whole rotation. It's really compelling to look at, and I could look at this forever. It's always intriguing, and it always holds up, and it's always surprising. And talk about surprising, look at this antique fork. Look closely. Are there 2 tines, or are there 3? In order to figure it out, we have to understand what happens when we take small features and combine them to make a global percept. We'll talk about this illusion and others like it in our next episode. Take a look at this. It's always been one of my favorites because my brother showed it to me when I was a little kid. And he showed it to me and said, look at the triangle. It looks like an ordinary object. But then he said, look, what happens if you cover all of it but this angle right here? You look at it and you say, oh, that's a 90-degree right angle. Now you cover up the next portion of the triangle. Hey, that angle is also 90 degrees. Then you do it again for this angle. And clearly, that one's 90 degrees. Then you pull it back, and you see the whole object again. And though every corner in that display makes sense, the whole object together doesn't. It makes sense, and then it falls apart. By adding more detail, you can make the object feel even more real in a three-dimensional sense. So here it is, where the joints are put together, and you can see the screws, so you feel like you can assemble it just like you got that flat pack from IKEA. But when you start putting the joints together, you could put it together here, you could put it together here, or you could put it together here, but it would never work all together, just like most of the furniture I try to assemble. These types of illusions are often associated with Roger Penrose, who made this object and another object called an impossible staircase. In the impossible staircase, just like the impossible triangle, all the cues make sense locally. And as you follow around the staircase, each of the steps make sense. If you start going down the steps, you always keep going down. But if you were to start moving up the step, you would always keep going up. The Dutch artist M.C. Escher was greatly influenced by Penrose. They corresponded frequently. Here he has monks perpetually walking up and down the steps of their monastery, going nowhere, as Escher observed. Here is a picture where he plays the game. Instead of people walking up the stairs, there's water flowing up to the top, then flowing down, and then starting over again. This, of course, would be impossible to do in the real world. But when you translate a three-dimensional world to a two-dimensional object, suddenly funny things begin to happen. You can make the impossible become seemingly possible. Whenever we look at something for the first time, our eyes will roam around the scene, trying to make sense of what we are seeing. Our brains are trying to figure out the relevant information to construct a perception that is both simple and meaningful. Most of the time, thanks to a lifetime of experience, our brains can arrive at an answer almost instantaneously, except when the details don't fit. So take a look at this object. It's sometimes called a devil's fork or a blivet. It's 3 tubes coming out of a base. Well, at least it looks like there's 3 tubes. But look what happens when you cover up this end. The base only has 2 parts coming out of it. If you cover up the base, it's clearly 3 tubes. It's incredible. Once again, the local cues tell you about what's important at that particular part. But when you start trying to combine them, things start falling apart. Our visual system has these 2 sources of information. It tries to make sense of them, but they're conflicting with each other. We have to make a decision. Take a look at this blueprint. It looks impressively technical. Almost certainly drafted by an engineer, someone who knows what they're doing. It looks as if it should fit together, doesn't it? But of course, like the ready-to-assemble impossible triangle, this can't be made either. The prongs of the threaded blivet, the orientation of what's called a Penrose frame, and the fiendishly impossible hex nuts. Every element would have you scratching your head within seconds. Here's another head scratcher. Known as the Ames trapezoid, it looks as if the window frame is gently swinging back and forth. Would it surprise you to know that the entire frame is rotating anti-clockwise? Don't believe me? Well, let's put a small cube on the moving stage to see whether the trapezoid is oscillating or rotating. Clearly, the whole assembly is rotating, but even though we know that, it still looks as if it's oscillating. It's another example of local cues overwhelming the global reality. Finally, I want to show you some of the fantastic work of my friend Kokichi Sugihara. His unique twist on the impossible object phenomena is to create objects that you can make and hold, but which appear to behave impossibly when seen in a mirror or viewed from a specific angle. His illusions often seem to defy common sense. Look at this. It seems impossible, doesn't it? Seen one way, it appears to be 2 rows of short cylinder tubes, 6 in all. But the reflection of the object appears to be 3 rows of square tubes, 8 in total. Same object, 2 very different images depending on the angle which you view them. And when Sugihara rotates the objects in front of your eyes, no video trickery involved, the situation is reversed. The square tubes are now in front of the mirror, but the reflection is showing cylinders. He created a number of these ambiguous objects, each more baffling than the one before. Sugihara's academic background is a mathematician, but he became interested in illusions when he realized the same 3D object in the real world could cast dramatically different images onto our 2D retinas. His calculations produced the assembly plans for a wide range of bizarre objects which, when viewed from a certain specific viewpoint, seem regular and ordinary. These 4 pillars seem to be vertical. But look at what happens when we thread a solid red rod between them. How does this happen? The pillars weren't vertical after all. Viewing angle plays a key role in many wonderful illusions. Here's one of Sugihara's that baffled many viewers on the internet. The balls that seem to be defying gravity by rolling uphill aren't rolling uphill at all. It just appears so because of the particular way he constructed the cardboard ramps. And most importantly, the illusion only works from one specific point of view. One of Sugihara's most recent illusions is this magical garage. Notice how the garage roof changes shape as he rotates the platform. When he picks up the object, you can see that it is a very complex shape, which depends on the viewing angle to produce either a convex curve or a corrugated roof. And you can't not see the illusion. Brilliant. Psychologists refer to this as an accidental viewpoint. The illusion only works from one specific point of view. In the next episode, I'll be showing you how viewing angle has played a role in visual illusions since the beginning of history. See you then. In this episode, we'll be looking at illusions that depend on a particular point of view for their full effect. It's an approach to visual illusions that is centuries old. Take a look at this. It is the Roman street scene in the famous Teatro Olimpico in Vicenza, Italy. It feels like it stretches on for hundreds of meters. You can imagine strolling down its length. But in point of fact, the street is only a couple meters long. But the artist, Andrea Palladio, used visual cues to make it seem as if it's going out for ages. Palladio's trick was to employ a steeply sloping floor at the rear end of the stage to represent the receding street and the buildings that line it. For centuries, artists have distorted 2D images to achieve certain 3D effects. It's called anamorphic art. A famous example of anamorphosis is Hans Holbein's painting, The Ambassadors. It shows 2 wealthy men standing in a room filled with treasures of their adventures. But at the bottom of the painting is an ominous white and gray streak, which, when viewed from a particular angle, resolves itself into a three-dimensional looking skull. The painting hung over a grand stairwell for many years, perhaps serving as a warning for those who passed by. Any 2D image can be distorted in this way. Look at what's happening to me right now. It's called an affine transformation, in which every part of the picture is distorted in a similar way. Even my wife and children wouldn't recognize me now. But I'm still there. If you run the affine transformation reverse, the indecipherable blur returns to the original image, just like Holbein's skull. Someone who knows all about the affine transformation is English artist Julian Beever, sometimes known as the Pavement Picasso. Julian Beever creates artworks out of chalk on sidewalk, so that when you're looking at them from a particular point of view, the artwork looks real and lifelike with depth. But if you look at the artwork from another perspective, the objects in the scene actually extend over hundreds of feet and look really quite distorted. Of course, the next rain shower will wash it all away, which seems like a pity, but maybe that's part of the magic. No such fate awaits Stefan Papp's art. They are hyper-real images that look almost like you could pick them up. But like the other illusions we've seen today, these only work when seen from one specific point of view. Watch as the artist rotates his sketches. They pass through a stage where the images are thoroughly distorted. And then, when properly aligned, the picture seems properly oriented again, and in 3 dimensions. We take our 3D perception of the world for granted. We think of it as interchangeable with reality. The light falling on the back of the eye is a 2-dimensional image. Our retinas in the back of the eye are flat. Where does our perception of 3 dimensions come from? The first thought people often have is that the 3rd dimension comes from the fact that we have 2 eyes, and each eye sees the world slightly differently. The brain can analyze that difference and convert it into the perception of depth. But you don't have to have both eyes open to perceive depth. Many depth cues can be inferred from a single monocular perspective. But these kind of depth cues can be manipulated to fool you. A great way to illustrate the limitations produced from a single perspective is the Ames room. In the Ames room, you have a single viewing point, and you look out to a room where the cues are such that it looks like a standard ordinary room. But in actuality, one side of the room has been extended so that it's actually farther away from the viewer than the other. But the room is painted so that it looks like a straight rectangular room. This can lead to some absolutely bizarre illusory effects. These 2 people are the same height, and yet the one in the left corner seems much smaller than the one in the right corner. This is because the one on the left is actually much further from the viewer than the one on the right, and is therefore casting a much smaller image on the viewer's retina. But all the other visual cues in the room suggest that it is a normal, rectangular space. So your brain concludes that the people must be of different sizes. Linear perspective is really important, and it alone can be used to create the appearance of depth. However, there are lots of cues that are available in the image, and we seem to be using all of them somehow. Take, for instance, shadows. Shadows tell you about depth, and you can see those illusions simply by themselves. Take a look at this one from Dan Kirsten's lab. Here is a ball. It's rolling across a box, and the shadow is right by it. So it looks as if it's rolling across the stage and rolling back. Now, I'm going to move the shadow so that it moves in a different direction from the ball. Now remember, the ball's moving in exactly the same way. Even though the ball followed the same path, now it seems to almost magically float in the air. So let's look at it again. Shadow with the ball. Shadow apart from the ball. In one case, the ball is on the ground, but simply by changing the shadow, one can create the appearance of floating. Finally, we've been talking about illusions which manipulate perspective in depth. Here's one that turns the tables. Indeed, it's called reverspective, a term coined by artist Patrick Hughes. It's very striking and demonstrates how powerful our 3D expectations of the world override what our eyes are telling us. While the wedges are extending out towards the viewer, the patterning on them has been made smaller and smaller, as would occur with increasing distance. Our visual system sees this size change and assumes perspective, but in the wrong direction. Once the depth is inverted, the motion inverts too, and the illusion is complete. So there's the dilemma. We have a brain, and the goal of that brain is to take the external world and to translate it into something that we see, perceive, and interact with. The more you move around, the better your perception is at figuring out what's out there. But if you only have one perspective, you're trapped. You can see things as someone wants you to see them from that particular perspective. It's often fun, it's often interesting, but it's always an illusion.